Chapter 55, Lung Volumes and Capacities. So in this chapter, we'll understand about the different lung volumes and capacities. So the pulmonary ventilation can be studied by recording the volume movement of air into and out of the lungs by a method called spirometry. So in this, you can see a spirometer. So basically, this is called the gas chamber. So through the mouthpiece, you actually inhale the air from this oxygen chamber and then you exhale into it, and then this floating drum, it based on your inhalation and exhalation, it kind of floats over the water, and the upward and downward movement of this drum is recorded on the recording drum, and that is how you get your graph with different values of your volumes and capacities. Okay, so now when we talk about pulmonary volumes, we have the tidal volume, which is the volume of air inspired or expired with each normal breath. It's about 500 ml in the adult male. And the IRV, inspiratory reserve volume, is the extra volume of air that can be inspired over and above the normal tidal volume. So it is about 3000 ml. Okay, expiratory reserve volume is the maximum extra volume of air that a person can expire at the end of a normal tidal expiration, that is after you have expired your tidal volume. So it is about 1100 ml, and RV is about 1200 ml. That means it is a volume of air that remains in the lungs, that it is a residual volume of air that remains in the lungs even after a forced expiration. Okay, it is about 1200 ml. And by adding up different volumes, we get different pulmonary capacities. Okay, so the inspiratory RV is nothing but the TV plus IRV. So it is the amount of air. So the TV is 500 ml and IRV is 3000. So 3000 plus 500, 3500 ml is the inspiratory capacity. So it is the amount of air a person can breathe in, beginning at the normal expiratory level and distending the lungs to a maximum amount. And then the functional residual capacity equals the ERV plus the RV. That means at the end of a normal expiration, how much air is remaining in your lungs. So normal expiration rate, so your TV is gone, residual volume is always there in the lungs. As it is normal, your expiratory reserve volume is still there in the lungs. So ERV plus RV is the FRC. And then the vital capacity, it includes the IRV plus the TV plus the ERV. Okay, it is the maximum amount of air a person can expel from the lungs forcibly after a forced inspiration. Okay, so then the total lung capacity is a sum of all the lung volumes that we have discussed. Okay, so all the pulmonary volumes and capacities are about 20 to 25% less in women than in men. This is the physiological variation. And another variation is that they are greater in large and athletic people than in small and asthenic people. Okay, so this is the actual graph. Okay, so this is your tidal volume, and then this is your IRV, this is your ERV. So this is your inspiratory capacity, this is your expiratory capacity, this is your functional residual capacity. Okay, and sorry, this is your functional residual capacity. Okay, and this is your total lung capacity. Next, so we have different abbreviations and symbols that are used. Okay, next, so when we talk about the different equations, we can understand that by the definitions itself. And so how do you determine the functional residual capacity and the residual volume and all that? So to measure FRC, the spirometer must be used in an indirect manner by means of helium dilution method. Okay, so because the value of FRC changes markedly in some types of pulmonary disease, it is important to measure this capacity. Spirometer cannot be used in a direct way to measure the FRC because the air in the residual volume of the lungs cannot be expired into the spirometer. So spirometer has to be used in an indirect manner. So spirometer of known volume is filled with air mixed with helium. Okay, so before breathing in from the spirometer, the person expires normally. So the after the end of this expiration, the remaining volume in the lungs is equal to the FRC. Okay, so when you inhale from the spirometer, the gases in the spirometer mix with the gases of the lungs. As a result, helium becomes diluted. Okay, so the FRC is equal to initial concentration of helium in the spirometer minus the final concentration of helium in the spirometer by final concentration into the initial volume of the spirometer. Okay, so once the FRC has been determined, the RV can be determined by subtracting the ERV and as measured by normal spirometry from the FRC. Okay, TLC can also be determined by adding IC to the FRC. Next, so what are the functions of the respiratory passageways? So all these the air is distributed to the lungs by the way of the trachea, the bronchi, and the bronchioles. So the most important challenge is to keep them open, all these structures. So to prevent the trachea from collapsing, we have multiple cartilaginous rings that are complete anteriorly and slightly incomplete posteriorly. They extend about 5/6 of the way around the trachea. In the walls of the bronchi also, we have less extensively curved cartilaginous plates. Okay, but in the bronchioles we do not have the cartilaginous plates. So how are the bronchioles kept open? They are kept open by the same transpulmonary pressures that expand the alveoli and keep the alveoli open. Okay, so that is as the alveoli enlarge, the bronchioles also enlarge, but not that much. And then the muscular wall of the bronchi and the bronchioles. See, you have cartilaginous rings in the trachea and other parts. So in the bronchioles, what you have is you have smooth muscles in the muscular walls. Okay. So many obstructive diseases of the lung, they result from narrowing of the smaller bronchi and larger bronchioles because of excessive contraction of the smooth muscles. And what is airway resistance? See, there is resistance to airflow in the bronchial tree. So under normal respiratory conditions, air flows through the respiratory passageways so easily that less than 1 centimeter of H2O pressure gradient is sufficient to cause enough flow for normal breathing. The greatest amount of resistance to airflow occurs not in the minute air passages but in the bigger passages like trachea and larger bronchioles and bronchi near the trachea, because see, all the smaller passageways, they are in a parallel connection. Okay, so the effective resistance decreases, whereas these bigger pathways are in series connection, right? So their resistance is more. Next, determinants. What are the determinants of airway resistance? So we know that resistance is equal to 8 eta L by pi r power 4. So this is for radius, right? The resistance depends on your diameter. So muscle contraction and edema, they increase or decrease the diameter, including the mucus that collects within the lumens. And then it depends on the viscosity and density of the gas that is being breathed, and also the diameter of the airways, the tone of the muscles, and all that. Okay, so and what is the nervous control? So directly there is very little sympathetic innervation of the bronchioles. So sympathetic stimulation mainly depends on the release of epinephrine and norepinephrine into the bronchioles via the circulation, via the blood itself. Okay, so sympathetic stimulation causes bronchodilation and they act via beta adrenergic receptors. And next, parasympathetic constriction. So parasympathetic stimulation, they are derived from the vagus nerves. They penetrate the lung parenchyma. They secrete acetylcholine and they cause mild to moderate constriction of the bronchioles. So when there is a disease such as asthma, which already causes bronchiolar constriction, superimposed to parasympathetic nervous stimulation, it worsens the condition. So administration of drugs that block the effects of ACH, such as atropine, can be helpful in this situation. Okay, and next, local secretory factors may cause bronchiolar constriction. So as you already know, in anaphylaxis you have the release of histamine and slow reactive substance of anaphylaxis from the mast cells, and that they're released during allergic reactions in the lung tissues by the mast cells. So what they do is they cause bronchiolar constriction. Okay, and they actually they cause bronchiolar constriction. And the same irritants that cause parasympathetic constrictor reflexes, smoke, dust, and sulfur oxide, they also act directly on the lung tissues to initiate local non-nervous reactions that cause obstructive constriction of the airways. And one important thing to know is the mucus lining the respiratory passages and the action of cilia. See, all the respiratory passages are kept by a moist layer of mucus that coats the entire surface. It is secreted partly by the individual mucus goblet cells in the epithelial lining of the passages. Okay, so the cells that line the respiratory passages, each cell has about 200 cilia on the epithelial side, and they beat at a rate of 10 to 20 times per second. And this power stroke is always towards the pharynx. That is, cilia in the lungs beat upwards towards the pharynx, whereas cilia in the nose, they beat downwards towards the pharynx. So then when there is proper irritation, a cough reflex is generated and you can cough out the irritant substance. Okay, So next we need to talk about flow volume curves. So the definition is flow volume curves or loops are graphical representations of relationship between maximal flow rate and volume of gas during a forced maneuver. Okay, they can be used to measure the following. So the flow rates during expiration, okay, the upper part of this graph, peak expiratory flow rate, which is like the slope of this graph, okay, and also forced vital capacity. So flow rates during expiration, they include forced expiratory load 25, that is FEF 25%, that is the flow rate at which time the 25% of vital capacity has been expired, and FEF 50, that means flow rate at the time when 50% of tidal volume has been expired, and the FEF 75 similarly. And then maximum expiratory flow, that is when a person expires with a great force, the expiratory airflow reaches a maximum flow beyond which the flow cannot be increased anymore. This is the maximal expiratory flow. Okay, maximum expiratory flow. Next, peak expiratory flow rate. The maximum flow rate that is attained during a forceful expiratory effort is called the peak expiratory flow rate. See, this is the peak expiratory flow. Okay. Next, in many respiratory diseases, particularly in asthma, the resistance to airflow becomes extremely high during expiration. Okay, that is why there is wheezing during expiration. So sometimes this causes tremendous difficulty in breathing. This concept has led to this condition has led to the concept that is called maximal expiratory flow. So here you can see the effect of increased pressure applied to the outsides of the bronchioles. What happens is, when you increase the pressure and constrict the bronchioles, the air in it is pushed outside, but the air behind that segment which you have constricted, it cannot pass. Okay, so that segment, the air remains within it. So the same pressure compresses the outsides of both the alveoli and the bronchioles. So this pressure forces the air from the alveoli towards the bronchioles, but it collapses the bronchioles at the same time, which will oppose movement of the air to the exterior. Okay. So when you look at this graph, it is important to analyze the flow. So basically you have expiration here in the upper segment and inspiration here. So what happens is, in inspiration your volume, it increases. Okay, see, okay, not like this, your volume, it increases during inspiration. Okay, whereas in expiration your volume decreases. Yes or no? Okay, and then see, this is the total lung capacity, and after you expire, after you get maximum expiratory flow, the only amount that remains is your residual volume. So the difference between these is your vital capacity. Okay, and then the FVC, force vital capacity. And then what you also need to understand is what happens in obstructive and restrictive diseases. One mnemonic is, in restrictive diseases there is a right shift. So what happens is, in restrictive diseases you are restricting air from entering your lungs. So your residual volume decreases, your total lung capacity decreases, like this, it shifts to the right. Whereas in obstructive diseases, you are obstructing flow of air to the outside. Okay, so what air remains in your lungs, you are not letting it flow out. So there is increase in total lung capacity and also in residual volume. So there is a left shift. Okay, so that is what you can see in this graph here. Okay, in restrictive or constricted lungs, and in airway obstruction. Okay, and also the peak expiratory flow, it decreases in both conditions. Okay. So constricted lung disease or restrictive lung disease, they include fibrotic diseases of the lung, such as tuberculosis and silicosis, and diseases that constrict the chest cage, such as kyphosis, scoliosis, and fibrotic pleurisy. Okay. And obstructive disease, a classic obstructive disease is asthma. Serious airway obstruction also occurs in some stages of emphysema. Next, forced expiratory vital capacity and forced expiratory volume. Okay, so in performing the FVC maneuver, the person first expires maximally to the TLC and then inhales into the spirometer with maximum expiratory effort as rapidly as possible, so that you get RV. The total distance of the downslope represents the FVC as shown in the figure. Okay, you can see here. Now you can study the difference between both the records for normal lungs and partial airway obstruction. So if you see in normal lungs and partial airway obstruction, there is no difference in the total volume changes of the FVC. There is a major difference, however, in the amounts of air that a person can expire each second. Okay, see, in 1 second this much of air can be expired, but in obstructive disease only this much can be expired. Okay, so therefore it is customary to compare the recorded forced expiratory volume during first second with the normal. These graphs are hence important. So like this and like this slowly. And so FEV1 by FEC total percent is about 80%. Okay, in serious airway obstruction as in asthma, this value can decrease to less than 20%. So what is a closing volume? The closing volume refers to the lung volume that coincides with the beginning of airway closure in the dependent parts of the lungs during expiration. So in normal healthy individuals, closing volume is less than the FRC and above the RV. So closing volume, it can be measured by using a similar apparatus as is used to measure the anatomical dead space, that is by the Fowler's method. The person is asked to inhale deeply 100% oxygen from mid-inspiration, and then the person exhales this steadily into an analyzer that measures nitrogen continuously. The curve is plotted like this, okay? And from the TLC, you're expiring, and slowly your alveolar N2 concentration, it comes into the expired air. Okay, first you exhale out all the oxygen that you've inhaled, then you have nitrogen. Okay, and then slowly at the end, when you reach RV, just above the RV and below the FRC, you get your closing volume. Okay, that's it.